All right, and we are live. All right. I went full boomer here for like the last 25 minutes trying to get my stream key and my channel all situated, but I have to say I think Twitch has an excessive amount of security. I have 6 different emails regarding passcodes to get into this thing, and the password requirements are like nothing I've ever seen, which is probably why this platform operates in a superior fashion to so many others. But here we go. We're on lesson 10.5, which is going to be the angle relationships of circles. So there's a number of these that we're going to discuss this morning. The first one that we're going to discuss is the secant tangent relationship. Now there's secant tangent is done a few ways. The first secant tangent relationship that we're going to discuss has to do with when we have an intersection that is at a point of tangency. So write that down for you. Sorry, it's with the intersection. All right, so we do have our intersection at point of tangency. What it looks like is this. So I have the, of course, the software corrected circle. No, the video didn't freeze. I had to go get a straight edge from across the room because I need to create a tangent line. So I'm going to create that tangent line of a point of tangency, which we're going to name P. Remember that tangent line is going to be effectively where we're going to kind of like glance off of the circle, kind of ever so gently kind of tap the circle here, just at that one singular location. And we're going to call that point P. P is going to be our point of tangency, all right? This is going to be line AB, which is going to be our tangent line. And at that point of tangency, and I'm going to add a few other points so that we can identify our arcs, because we're going to have a few that are going to happen here. I'm going to create a secant line through that point of tangency, so like this. Oops. So this line PC, which is a secant line, and I have a few arcs here. So I have a minor arc PC, and then I have a major arc PDC, all right? With those, this is the secant tangent relationship. I have 2 types of lines. One is a secant, one's a tangent, and their intersection is at this point of tangency P. Very plainly, this is what we're gonna have here, is we have a couple of outcomes. What we've discussed so far is how to create an angle with a circle. So we did it from the center, right? We had the central angles. That was constructed through 2 radii. Then we had the inscribed angle, right? So I could actually create one of these, for example, like PD and then D to C, right? PDC, that could be its own inscribed angle, which is going to be 1/2 of PC, that minor arc that that chord I have there. So there's that, again, that minor arc PC as well. Its relationship, again, inscribed angle all the way across the circle. It's created by effectively two chords, not secants, but 2 chords. Because they have a terminating point, which is that vertex, in this case would have been D. Now I have created a whole different angle. So let's consider this angle I have right here, CPB or PBC. So the measure of that angle, BPC, has a relationship in that it is also 1/2 of the measurement of that arc PC. So we dealt with this in our last lesson where we had inscribed angles that had a relationship of 1/2 of the minor arc that they were intercepting, right? We're only intercepting a singular arc here, and then we have B, which is going to be, right, PB. B, that point is outside of the circle, but again, this angle is going to be have that relationship that's 1/2. Now, if I'm going to take the major arc with that obtuse angle, the same sort of relationship is going to exist. It's pretty straightforward, so there's not multiple things to memorize. That the measure of angle APC is going to be equal to 1/2 the measurement of that major arc that I have there, PDC. So, fun question here. If, hypothetically, that I had the measure of arc PC equal to 100, then what is the measurement of angle APC? Now remember, APC is the obtuse angle. PC has a relationship here with the acute angle, which is BPC. BPC is going to be a 50-degree angle, correct? Because it's going to be 1/2 of that arc. And remember, what do I have here with these the obtuse and the acute angle? But I have a linear pair, right? Pair of angles formed off of a line. Linear pairs are supplementary. So if I have a 50-degree angle, its supplement is going to be 130 degrees. And that would be the answer there. All right. Using our imaginations here a little bit. So we have discussed a few things. And I'm going to create 2 secant lines, which is what I'd like you guys to do on your papers right now while you're taking notes. But effectively this. What we've discussed so far is creating angles at the center. Very clearly here, we are not at the center. Center would be somewhere right around here, okay? We've also created angles that are on the circle, right? The vertex is on the circle, vertex at the center. But we haven't really considered, what about if we don't have our vertex there? Now we have the vertex on the circle, but not formed through 2 secants. We had one as a secant, one as a tangent. And then there's not really an alternative logically with a tangent, right? Inside of the circle, though that's going to come up. It can't happen in the circle. We'll see how else we can do it. But however else we could create angles really in a circle is going to be through the intersection of 2 secant lines, right? Which of course will also create chords within it. So let's go ahead and label these points here. I have line AB, and then I have line CD. And we're going to do a proof here, a real quick shorthand proof to give us a couple of angles here. So we have angles 1 and 2, okay? And figuring out how we're going to decipher what our angle measurements are going to be here, because there's a few things that we should be able to see right away, right? We have an angle here and here that are going to be vertical angles, and angles here and here that are vertical angles. So those angles are going to be congruent to each other, okay? What we do need to find is what 1 is and what 2 is, because if I know 1 and 2, I know those other 2 angles that are created inside of the circle due to the nature of vertical angles. So here's what we can do. We're going to do a proof here where I can create this auxiliary line here from A to D. So I'm going to create a chord at AD. And at that chord, I have 2 other angles here, okay? 3 and 4. And I've created a triangle. So remember what I have there. Gentlemen, I actually have the exterior angle theorem illustrated. It's this. If I have 3 and 4, 1 is going to be equal to the sum of 3 and 4. Probably heard somebody coughing, by the way, in the stream right there. If that was a cough or a sneeze, and it's because we're live in block 1 right now. They may have some questions. They are on their best behavior. There's actually a healthy amount of fear in their eyes, which is good. They know not to do anything inappropriate in the stream. So remembering the following, right? So we have 1 is going to be the sum of 3 and 4, okay? And now think about what we have here. The measurement of angle 3 is the following. The measurement of angle 3 is going to be equal to, remember, it is a inscribed angle, right? So what it's really going to be equal to is 1/2 of arc BD, right? This is the arc that intercepts it. So this was in our last lesson. So think about how we construct the measure of angle 4. Well, that's going to be 1/2 of, right, this guy, the intercepting arc, which is AC. So I can substitute here. So really what I have here is the measurement of angle 1 is going to be equal to 1/2 BD plus 1/2 of AC, arc AC, right? And then what I could really say here is that, well, I could take the measurement of angle 1 and I could factor out that 1/2. So I could say that it's equal to 1/2 of BD, arc BD, plus arc AC. So what I have here is effectively a theorem, right? Is that if I take any angle created through what's known as secant, with my intersection in the circle. All right? If I do that, I have the following. I can get the measure of angle 1 as taking 1/2 of the sum of these vertical, I always call them the vertical arcs. Okay, so thinking about the vertical angle I'd have right here, that relationship. So AC and BD. Think about how we do that for angle 2, right? Well, angle 2 is going to be the same thing. It's the results of, it's formed as the results of 2 secants inside of a circle, right? It's not at the center. And then we're going to say, well, here's one vertical arc. That's the intercepting arc effectively for 2, and the arc that's vertical to it. So BC and AD. So let's do a practice problem. Should be straightforward. Ready? Let's create a circle. And I'm going to create 2 chords that do not have an intersection at the center. If I continued those chords not terminating on the circle, I'd of course have secants. Without any of that said here, right? So I have a 94-degree angle. I have an 80-degree arc. And I have an arc that's x degrees. And we're going to solve for x. That's what's given. Well, remember, 94, and I'm going to call this y, angle y. That's the linear pair with 94. Well, of course, y we will know is equal to 86. Linear pair, right? Supplementary. So 180 minus 94 is going to give us 86. So what we should say is that angle y is equal to 1/2 of those 2 vertical arcs that we have, 80 and x, right? So we have 80 plus x. But we know what y is, right? It's 86 equal to 1/2 of 80 plus x. Now we have some, we're just doing algebra, right? To solve for x. We have some options. We can distribute the 1/2, or we can multiply both sides by 2. I think that's going to be a better outcome for us. So multiply both sides by 2, so we'll get 172 is equal to 80 plus x, subtract 80 from both sides, and we're going to get that x is equal to, according to your calculator, 92 degrees. All right, so for your next test, you get a note card. And some of you guys are thinking, well, you know, it hasn't been bad so far because we've got a couple of, you know, like the inscribed angle effectively has that same relationship as secant tangent. And then now we have this thing, and we did a little proof for it to figure out what secant inside the circle was. But there's a number of relationships that we are going to illustrate here. And I'm only going to do a couple examples afterwards. We're going to find effectively the identify what the relationship is. But when you guys do this in your notes right now, what you need to do is the following. Side by side by side, you need 3 circles. So you'll need 3 circles that are close to identical. I'll show you guys what we're looking for here. Let's go ahead and construct this. Let's get a little bit over here. And I can move this one. Again, as I said, side by side by side. 3 things side by side. All right. First one. We are now in the realm of creating intersections, not just in the circle. All right, so we've done that each way that we can. We've done it on the circle. We've done it in the circle. We've had our central angle, our inscribed angles, our secant tangent on the circle, secant in the circle. Then now we're going to do the following. So we're going to take a point exterior, right? And this will be our point of intersection for each of these, satellite to that circle, right? So we're going to call that point A. And I'm going to effectively draw a very similar figure each time. Just changing a little bit what I'm doing. So we've done, let's repeat effectively what we did earlier, which is we're going to have secant. Oops. Really trying to get a tangent line here. I'm struggling. Let's see here. There we go. And thinking that lines that look tangent are tangent. That's just something you're going to see in your textbook. So I'm going to make sure that I kind of really highlight that point of tangency. So this is going to be B and C. And this is going to be D. So B and C are those points of intersection, C the point of tangency. Think about what we had here. We had one secant line and one tangent line. This relationship is called secant tangent. All right, next, we're going to take point A. This one's actually fairly, a little bit easier, I think, to draw because don't have to draw a tangent line because I can draw a secant and then yet another secant, where they're going to share that, oops. I'm going to widen that angle up a little bit this time. So again, I have B and C, and then I'm going to have D and E, where they're going to share that point A as their vertex, and I have 2 secants, so this is called secant. Next relationship, we've done secant tangent, we've done secant. We cannot do tangent, 2 tangents with the intersection inside on the circle, right? We just can't. It'd just be right, because if we have that straight line, right here, let's draw a tangent line. Just consider the nature of I always hate the notion of the straight angle. We've talked about this in class before. I don't really ever identify that that figure, but if I'm going to create that tangent line, right, and this is going to be point B, there's no way for me to be at that point of tangency and close that, like here, if I try to do this and make an angle, right? That's not going to have any real, like, there's no way to make it tangent, right? Simultaneously. You see what I'm saying? Is that as soon as I close this thing at all, I'm creating a second point of intersection somewhere on that circle. I could create another tangent outside of the circle. That's going to be totally irrelevant to the circle, though. There's no relationship to discuss because there's no real intersection except for at that one point. So we have no real point of reference. So here, though, I'm going to create another line of tangency from A, and that point of tangency is going to be C. And again, I have two tangent lines, so this relationship is referred to as tangent-tangent. Again, you are getting a 3x5 note card for your next test. I will provide it for you. You may want to write down some of these relationships because they all really have the same construction, okay? So I'm going to go through this so you guys can see how this is done. It's going to be that the measure of each angle, the measure of the angle outside of the circle A, is going to be dictated by the 1/2 of the difference of the two arcs that are formed, the outer arc and the inner arc. So it's going to be A is equal to 1/2 of the measure of arc DC minus the measure of arc BC. In other words, it's 1/2 of the outer minus the inner. Same deal. Measure of angle A for secant. Same. It's going to be 1/2 of the measure of DE minus BC, the outer minus the inner. And then for tangent, same deal. The measure of angle A is equal to, and I have, real quick, I'm going to put I need another point here. I'm going to call it D, just so I can differentiate between the major and the minor arc. So I'm going to have here the measure of angle A is equal to the arc, measure of arc, the outer, which is the major arc, BDC, minus the inner arc, which is the minor arc, BC. All right, fun times. Let my friends who are in front of me right now copy that down. So we have some examples. Here we go. Here's your diagram. We have a circle. Please copy this to the best of your ability. A, B, C, and I've oriented this a little bit differently, D and E. Again, don't worry about what it looks like. Worry about what the diagram actually says. It says this guy's 100 degrees, this arc DE. It says that this is X degrees, that's arc BC, and that this angle right here is 35 degrees. We're going to solve for X. Remember, the measure of angle A is going to be equal to the outer arc DE minus the inner arc BC. So in other words, angle A, which is 35, is equal to 1/2 of that outer arc 100 minus the inner arc BC, which is X. And we solve, right? Rather than distributing, because I don't want to distribute to that negative X, right? I can just multiply by 2. So I'm going to get 70 is equal to 100 minus X, subtract 100 from both sides. So I get negative 30 is equal to negative X. So therefore, I have 30 is equal to X. Pretty straightforward. Next. I have a point S exterior to a circle here. And here I'm going to construct two tangent lines. On your homework in the book, it's going to tell you lines that appear to be tangent are tangent. So you can make that assumption just based upon what the diagram looks like, okay? So here we go. S. I have center R. This is circle R, where we're going to solve for x. I have a point of tangency. I have a point of tangency. Okay, let's see if I can make these guys, these radii right here, actually do what they're supposed to. This guy's point Q, this guy's point P, and this is 124 degrees. And this is x. That's all that we're given. We're given a central angle. That's it. Well, how would we solve? Well, we know that x is going to be equal to 1/2 the outer arc, right? Which is a major arc, minus the minor arc. Well, this is a central angle, right? So that central angle is going to be the same as the intercepting minor arc. So arc PQ is 124 degrees. So how much is the major arc? Well, it's the difference of 360 and 124, which is 236 degrees, right? Because the whole circle's got to be 360. So now we have all the numbers we need to work with. 236 minus 124. X is equal to, let's keep evaluating, right? 1/2 of 236 minus 124 is 112. So x is 56 degrees. Moreover, textbook details how to find this, right? Which is going to be that angle S is going to be equal to 180 minus the measure of the central angle. I think that theorem is fine, right? When we have secant tangent, that the exterior angle is going to just be equal to the difference of 180 and the central angle. It's true. That's great. But I prefer just to kind of continue to have the same problem solving process. Okay. So 2 ways to go about it. If you want to write down that theorem or utilize that on your homework. Last example for today is the following. Circle. Have point D, exterior. We're trying to create a tangent line, so do your best to do so as well. Circle O. Let's put C. And then I have AC and CB, right? This is X degrees. Okay. This is 42 degrees given to us. BC is 222 degrees. Well, remember, right here what we have is we know that angle C is going to be equal to 1/2, right, of arc AB. Okay. Well, think about this, guys. Remember, how do you find arc AB? Well, AB effectively opens up to the following. Look, this and this, right? AOP, well, remember what our relationship was in the previous problem, right? That we had this angle right here is going to be supplementary to that central angle. So the central angle is going to be 138 degrees because it's a supplement with this guy right here. If I know that angle is 138, then I know arc AB is 138. So angle C is going to be equal to 1/2 of 138, right? Which means angle C is equal to 69 degrees. And there we go. Well, if I'm solving for x, remember I could do it like this. That x is equal to 1/2, and this is another thought process to the thing, of AB, right? Well, think about it. I have 42 is equal to 1/2 of the difference of that outer arc, the measure of arc ACB, and the measure of arc AB. Okay? Which, again, we have 42 is equal to 1/2, if you effectively distribute ACB times 1/2 AB. But remember what 1/2 AB is, right? It's just x. So effectively what I'm saying is that 42 is equal to 1/2 of the measure of ACB, right? And if I already know what ACB, right? So I'm going to take ACB, which is 222, right? Okay? And to substitute, right? By substituting, and then we're just working out some algebra, right? That's going to be 111. Subtract 111 from both sides. Again, negative 69 is equal to negative x, meaning that 69 is equal to x. So you could do the problem really either way. This one is shorter, right? So utilizing that theorem where we have the supplement between the angle exterior when you have tangent to the central angle, kind of shortens up your problem solving process. Or again, we could just back this thing out, utilize the relationship of tangent being 1/2 of the difference of the outer arc and the inner arc. That's all I've got for you guys. I'll have this posted up on Canvas, and if you have any questions, please contact me.